you are falling. Right now, at this very moment, you're plummeting through a hole in space, 2 billion light years wide, and until recently, almost nobody knew. In 2013, 3 astronomers made a discovery that would shatter our understanding of the cosmos. Ryan Keenan, Amy Barger, and Lennox Cowie were mapping the universe when they noticed something impossible. They examined 35,000 galaxies across billions of light years, and the numbers were wrong. Everywhere they looked near Earth, galaxies were missing. Not just a few 20% fewer than there should be. The pattern stretched outward in every direction for 1 billion light years, forming a sphere of cosmic emptiness with us near the center. This wasn't a small gap between galaxy clusters. This was a void on a scale that shouldn't exist. They called it the KBC Void, using their own initials. But there's nothing casual about what it represents. The implications were immediate and unsettling. If we live inside such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure cosmic expansion, are we seeing the truth, or a distorted local version? The void might explain one of cosmology's greatest mysteries, the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they observe the ancient universe or the nearby universe. The numbers disagree by 9%. Both measurements are incredibly precise. Both should give the same answer. They don't. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it, adding extra velocity to their motion. The local expansion would appear faster than average. Suddenly, the conflicting measurements made sense. We're not measuring incorrectly. We're measuring from inside a hole. But this realization raises an uncomfortable question cosmologists still grapple with. If our location is this unusual, can we trust anything we think we know about the cosmos? Cosmic voids aren't truly empty, which makes them stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than average. The void around us has roughly 15% of normal cosmic density. If a typical region has 10 galaxies in a given volume, the same volume in our void might have only 1 or 2. Between these lonely galaxies stretches space containing mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. The void stays a void. This emptiness has profound consequences. Gravity is already the weakest fundamental force, requiring enormous masses to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure accelerating cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing expansion. Inside voids, gravity loses that tug-of-war decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward while filaments of galaxies around them act as walls. Scientists confirmed this through careful observation, measuring how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward, the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls from the mountains toward the valley. But since we're talking about space rather than terrain, that pull makes galaxies fall outward, not inward. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity causes less gravitational redshift, showing up as cold spots in temperature maps. These cold spots line up perfectly with where we observe large voids today. This alignment isn't coincidence. it's physics. The universe isn't a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups extending for hundreds of millions of light years. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Only when scientists began measuring galaxy redshifts systematically in the 1,970 seconds and 80 seconds did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate distances by measuring how much expansion had stretched light toward redder wavelengths. Suddenly, the distribution snapped into focus. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show filaments that twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter wasn't perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density, some regions slightly denser, others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The Milky Way isn't at the center of the KBC Void, but it's close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. The void extends outward for 1 billion light-years in every direction, making our offset relatively small. We sit well within the underdense region, surrounded by low-density environment in all directions. This position has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. The Hubble tension would not exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor, Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Here's the paradox. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC Void. How can a supercluster exist inside an underdense region? The answer lies in how density is defined. The KBC Void is underdense compared to the cosmic average when measured over very large scales. But it's not uniformly empty. It contains localized concentrations of matter, like Laniakea, that are denser than their immediate surroundings. The local group is also influenced by another nearby void called the local void, which extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by gravitational pull from denser regions beyond. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. Galaxies aren't just sitting in an empty region, passively expanding with the universe. They're actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond. Every measurement you've ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we're measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number telling us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer: about 67 kilometers per second per megaparsec. The second method looks at nearby objects with known brightness, specifically type Ia supernova and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing actual brightness to apparent brightness, scientists calculate distance. Combining distance with redshift gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They don't. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, less than a 1 in a million chance it's random variation. The KBC Void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we're measuring within the void. The void's low density means less gravity pulling back on expansion. Matter from denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. We're not measuring the universe's true expansion rate. We're measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed. But here's where it gets uncomfortable. If the void explains our local measurements, then those measurements don't tell us about the universe as a whole. They tell us about our weird local environment. The cosmic microwave background method is unaffected by the void because it probes the early universe long before voids formed. That measurement might be the accurate one for the universe's global properties. This means most headlines about the accelerating universe and dark energy might be describing a local phenomenon rather than a universal truth. We've spent decades building cosmological models based partly on local expansion measurements, and those measurements might be systematically biased by our location. The Hubble tension creates another crisis: the age of the universe. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. But if the local expansion rate measured at 73 kilometers per second per megaparsec represents the universe's true rate rather than a void-distorted value, the universe has been expanding faster throughout its history. A faster expansion means the universe reached its current size in less time calculations show. This would make it about 12% younger, roughly 12.7 billion years old. That may sound like a small difference, but it creates major conflicts. The oldest stars in globular clusters appear to be about 13 billion years old, based on stellar evolution theory. You cannot have stars older than the universe itself. These stellar ages come from understanding how stars evolve over time. By observing which stars have reached the end of their lives in a globular cluster, astronomers can estimate when all the stars formed. The oldest clusters show their most massive remaining stars are just barely still alive, indicating formation about 13 billion years ago. The Gaia space mission has revolutionized these measurements by providing precise distances to globular clusters through parallax measurements. The improved measurements confirm the oldest clusters are indeed about 13 billion years old. If the universe is only 12.7 billion years old, the numbers simply don't work. The void offers a resolution. If it inflates our local measurements, the cosmic microwave background estimate of 13.8 billion years could be correct. The universe would be old enough for the observed stars to exist. This resolution requires accepting we live in an unusual location, which bothers some scientists philosophically, but it avoids requiring major changes to stellar physics or cosmology. Galaxies aren't stationary. They move through space in response to gravity from surrounding structures. These motions are called peculiar velocities, distinct from overall cosmic expansion. In standard cosmology, peculiar velocities should be relatively small and random on large scales. When you average over volumes hundreds of millions of light-years across, those velocities should largely cancel out. Observations tell a different story. Measurements show significant bulk flows extending to distances of 200 to 300 million light-years, reaching velocities of 400 kilometers per second or more, far higher than standard cosmology predicts. These flows are coherent, meaning galaxies across huge volumes are all moving in roughly the same direction. This suggests the presence of large-scale structure producing gravitational gradients. The KBC Void is exactly the kind of structure that could produce such flows. Material within the void is accelerating outward, toward denser regions beyond the void's edges. The Cosmic Flows Project has created the most detailed maps of bulk flows to date, and the observed patterns match predictions from models that include the KBC Void. When researchers simulate how galaxies should move if they're inside a large, underdense region surrounded by overdense shells, the predicted velocities and flow patterns closely match observations. The flows are strongest near the void edges where the density gradient is sharpest. They're directed outward from the underdensity toward surrounding filaments. The magnitude depends on the void's depth and size. A 20% density deficit extending 1 billion light-years produces flows of about 400 kilometers per second, exactly what is observed. Standard cosmology without a void struggles to explain these flows. Simulations based on lambda-cold dark matter predict bulk flows should decline rapidly with scale. By the time you average over 200 million light-years, flows should be under 100 kilometers per second. The observed flows are 4 times larger. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC Void threatens to shatter it. The principle states the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special. Isotropic means the same in all directions. These assumptions simplify the mathematics of cosmology enormously, allowing scientists to model the entire universe using relatively straightforward equations. The principle has been remarkably successful, accurately describing many observations. But the KBC Void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that's a huge inhomogeneity. Even on cosmic scales, the void isn't small. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth wasn't the center of the solar system. Later observations showed the solar system wasn't the center of the galaxy, and the galaxy wasn't the center of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, but there is no center because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large underdense region, our location is unusual by definition. Voids are common, but most are smaller. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical realization of the universe's structure, you might not find one anywhere in the observable cosmos, yet we're in one. Defenders argue the void doesn't actually violate the principle, because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than assumed. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During inflation, the universe expanded exponentially for a tiny fraction of a second. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales, creating slight variations in matter and energy density. In some regions, density was a tiny bit higher than average. In others, it was lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding at a much slower rate. Matter began clumping together under gravity, amplifying the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, creating a positive feedback loop. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away, the underdense regions became even emptier. These underdense regions evolved into voids. The process is called gravitational instability. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. Satellites have mapped temperature variations across the entire sky. Hotspots correspond to regions that were slightly denser, cold spots to regions slightly less dense. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or filament. But probability distributions matter. Small voids should be common. Medium voids, less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category. One analysis calculated that a void of its size and depth represents a 10 sigma deviation from expected density. In statistics, a 5 sigma result means less than a 1 in a million chance of being random. A 10 sigma result is incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one such void. Yet here we are, living in one. When you picture the universe, you probably imagine a sky full of stars and galaxies. But reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This isn't just empty space in the sense of vacuum between stars. It's empty in the sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many contain large amounts of neutral hydrogen gas that hasn't yet condensed into stars. They're galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present at about 15% of cosmic average density. Additionally, voids contain dark energy, which appears uniform throughout space. Because dark energy doesn't clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Billions of years in the future, the universe will be even emptier than now, with voids occupying an even larger fraction of total volume. Cosmic voids are the best places in the universe to study dark energy because they're the only regions where dark energy dominates completely. In dense areas, like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together despite the universe expanding around them. Even in filaments, gravity is still relevant, slowing expansion. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. The voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. This makes voids natural laboratories for measuring dark energy's strength and properties. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy. It behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself. Or it could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different times. Voids provide a cleaner signal for these measurements than dense regions. In dense areas, gravity complicates everything. Local gravitational pull from nearby masses affects galaxy motions, making it hard to separate cosmic expansion from local effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or changes. If dark energy is stronger in voids than elsewhere, or if it was different in the past, that would show up as deviations from expected void expansion rates. The expansion history of voids also encodes information about dark energy. Voids have been growing for billions of years, and their current size reflects that entire history. By modeling how a void should grow over time given different dark energy properties, scientists can compare predictions to observations and constrain what dark energy must be like. The void's existence has led some scientists to question whether gravity itself needs revision. The standard theory is Einstein's general relativity, formulated in 1915. It has passed every test for over a century. But if the KBC Void is too large and too deep to arise naturally in simulations based on general relativity and lambda-cold dark matter, perhaps gravity doesn't work exactly as Einstein predicted on the largest scales. Modified Newtonian dynamics, or MOND, is the most prominent alternative gravity theory. Proposed in 1983, MOND suggests gravity behaves differently when accelerations are extremely small. At high accelerations like those on Earth, gravity follows Newton's laws and Einstein's corrections exactly. But at tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. In MOND cosmology, structures form more efficiently because enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids. Computer simulations using MOND gravity naturally create voids as large as the KBC Void without requiring unusual initial conditions. The statistical improbability disappears. However, MOND faces serious challenges. It struggles to explain the cosmic microwave background temperature fluctuations. MOND also cannot easily account for gravitational lensing observations where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter, plus MOND's modification can provide, suggesting dark matter is still needed. Another class of modified gravity theories involves changing how gravity propagates over large distances. Some of these theories predict gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. If velocity patterns deviate from general relativity's predictions, it could indicate modified gravity at work. The debate between modified gravity and standard cosmology remains unresolved. Proponents of modified gravity argue that repeatedly finding structures too large or too rare according to standard models indicates the models are wrong. Defenders of standard cosmology argue modified gravity theories have their own problems and prefer to accept we live in an unusual location rather than overthrowing a century of successful gravitational physics. The term Hubble bubble has emerged to describe a troubling observational pattern. When astronomers measure the Hubble constant using nearby objects within about 2 billion light-years, they get higher values around 73. When they use objects farther than 2 billion light-years or rely on cosmic microwave background data, they get lower values around 67. The boundary at roughly 2 billion light-years is suspiciously close to the edge of the KBC Void. This has led researchers to propose that measurements within the void are affected by its presence, creating a bubble of biased observations. Only by looking beyond the bubble can we see the universe's true expansion rate. This hypothesis makes a clear prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look farther out, approaching and crossing the void's edge, the measured value should decline toward the cosmic average. This is exactly what recent observations are beginning to show. Studies using supernovae at various distances find that the inferred Hubble constant decreases with redshift. The trend isn't yet definitive, because measuring distances to very distant supernova is challenging, but the direction matches predictions from the Hubble bubble hypothesis. If the bubble is real, it creates a significant problem. Most measurements of local expansion necessarily use nearby objects because those are the only ones we can observe in sufficient detail. We're trapped inside the bubble, unable to step outside our local environment to see what the universe truly looks like. Breaking out of the bubble requires observing objects beyond 2 billion light-years with comparable precision to nearby objects. Space telescopes like James Webb can observe distant supernovae with unprecedented detail. Ground-based observatories with enormous mirrors are discovering quasars and other bright objects at extreme distances. Early results suggest the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. Multiple independent lines of evidence point to the same conclusion. Our local environment within about 2 billion light-years differs systematically from the universe at large. The KBC Void isn't the largest underdense region known. That distinction belongs to the Eridanus supervoid, located in the constellation Eridanus. This void is roughly 1.8 billion light-years across, making it comparable in scale to the KBC Void. What makes the Eridanus supervoid particularly intriguing is how it was found. Astronomers didn't discover it by counting galaxies. They discovered it by noticing an unusually cold spot in the cosmic microwave background temperature map. This cold spot, about 10 degrees across on the sky, corresponds to a region where the microwave background is about 70 microkelvin cooler than average, much colder than typical fluctuations from the early universe. The cold spot was discovered in 2005 and puzzled cosmologists because its size and temperature deficit are statistically unusual. Random fluctuations from the early universe should occasionally produce cold spots, but one this large and cold is rare, occurring in only about 2% of simulated universes. A more conventional explanation emerged when astronomers surveyed the galaxy distribution in the direction of the cold spot. They found evidence for a large underdense region roughly aligned with it. Light from the cosmic microwave background passes through this void on its way to Earth, experiencing the integrated Sachs-Wolf effect. As light traverses the expanding void, it loses energy, showing up as a temperature deficit. Calculations show a void of the Eridanus supervoid's size and depth can account for about half the observed cold spot temperature anomaly. Current estimates place the deficit at about 20 to 30% compared to cosmic average, similar to the KBC Void. If both the KBC Void and Eridanus supervoid are real and as extreme as measurements suggest, it raises the likelihood that such voids are more common than standard cosmology predicts. Two large supervoids in the observable universe might still be consistent with lambda-cold dark matter if you allow for statistical variance. But finding 3 or 4 would become increasingly difficult to explain. Galaxies inside cosmic voids grow up in profound loneliness. Unlike galaxies in dense clusters that interact frequently with neighbors, void galaxies evolve in isolation. This environmental difference shapes everything about them. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They have lower masses, containing fewer stars and less overall matter. Many are classified as dwarf galaxies, barely massive enough to hold onto their gas against outward pressure from star formation. Their isolation means they rarely experience galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. The star formation rate in void galaxies is generally lower than in cluster galaxies, but there's a surprising twist. While most void galaxies form stars slowly, a higher fraction are starburst galaxies experiencing intense, short-lived periods of rapid star formation. This seems paradoxical until you consider gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that haven't yet been converted into stars. In dense environments, interactions with neighboring galaxies can strip away gas or trigger star formation, depleting the reservoir. In voids, galaxies retain their gas longer. When star formation does ignite, perhaps triggered by internal processes, there's plenty of fuel available. The morphology of void galaxies also differs. Most are late-type spirals or irregular galaxies rather than elliptical galaxies. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms. Some void galaxies show remarkably undisturbed morphologies with smooth disk profiles and regular rotation patterns. One puzzling aspect is chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they release these elements into space. Subsequent generations incorporate these elements, gradually enriching the galaxy's overall chemical composition. Void galaxies, with their slower star formation rates, should have lower chemical enrichment. Observations confirm this to some extent. Void galaxies tend to be more metal poor, but the difference isn't as large as expected, suggesting chemical evolution is more complex than simple models predict. Dark energy is accelerating the universe's expansion, and that acceleration has dire implications for the far future. As space expands faster over time, structures not gravitationally bound together will drift apart and eventually lose all contact. This process is already happening, but it will intensify over the coming billions and trillions of years. Voids will expand faster than the universe as a whole because they contain less matter to resist expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact, as space between them expands faster than light can cross. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC Void can still see surrounding filaments and clusters in the distance. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us, will shrink over time. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies with fewer and fewer neighbors visible. The cosmic microwave background will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually, it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty, except for their local group. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to trace acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy. This merged galaxy will be the dominant structure in our local group. But the local group itself will become increasingly isolated. Other nearby groups will recede beyond our cosmic horizon within tens of billions of years. The merged galaxy will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars, and black holes. The night sky will darken as fewer stars remain active. On even longer timescales, trillions of years into the future, stars will become rare as their fuel is exhausted. Eventually, even black holes will evaporate through Hawking radiation. The final state of the universe will be a diffuse sea of particles and radiation expanding forever into darkness. Voids will have consumed everything. We are inside a cosmic hole 2 billion light-years wide. This isn't metaphor or speculation. This is observation. The KBC Void is real. Its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it makes us unusually positioned in the universe, these questions remain open. But one thing is certain. The universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. We are cosmic castaways drifting through a desert of space, measuring a universe that may not be what it seems. Every telescope we point at the sky, every measurement we make of cosmic expansion, every conclusion we draw about the universe's fate, all are filtered through this lens of emptiness. The implications extend beyond mere numbers and statistics. They touch on something profound about the nature of scientific knowledge itself. For centuries, we've built our understanding of the cosmos on the assumption that our vantage point is ordinary. that what we observe from Earth represents universal truth. The cosmological principle wasn't just a mathematical convenience. It was a philosophical statement about our place in the universe. The void challenges that assumption at its core. If we occupy an unusual location, then the very measurements that form the foundation of modern cosmology might be systematically biased. The expansion rate we measure, the age of the universe we calculate, the properties of dark energy we infer, all could be distorted reflections of a local anomaly rather than cosmic constants. Yet there's something almost poetic about our predicament. We live in a universe that is mostly empty, and we happen to reside in one of its emptiest regions. The cosmos has organized itself into a structure where matter is the exception and void is the rule. In a sense, by living in a void, we're occupying the most typical environment the universe has to offer, not the crowded galaxy clusters that catch our attention, but the vast expanses of near-nothingness that define the cosmic landscape. The resolution to these mysteries will come from looking deeper into space, farther back in time. Next-generation telescopes and surveys are already beginning to map the universe with unprecedented precision. The Vera Rubin Observatory, with its massive mirror and wide field of view, will discover millions of galaxies and trace the cosmic web in extraordinary detail. The Euclid Space Telescope is mapping the geometry of the universe, measuring how dark energy shapes the expansion of space across billions of years of cosmic history. These instruments will allow us to observe galaxies well beyond the void's edge, providing measurements untainted by our local environment. They'll map the three-dimensional structure of the universe across vast volumes, revealing whether large voids like the KBC Void are rare anomalies or more common than we thought. They'll trace the velocity fields of galaxies across billions of light years, testing whether the bulk flows we observe locally extend farther or fade away as standard cosmology predicts. Within the next decade, we should have a definitive answer to whether the Hubble bubble is real. If measurements of the expansion rate converge to the lower value predicted by the cosmic microwave background once we look beyond 2 billion light-years, the void hypothesis will be confirmed. The Hubble tension will be resolved, not by new physics, but by recognizing we were measuring from an unusual location all along. If, however, the tension persists even at great distances, if the universe continues to show conflicting expansion rates, no matter how far we look, then something more fundamental is wrong. New physics will be required. Perhaps dark energy evolves over time. Perhaps gravity behaves differently on cosmic scales than general relativity predicts. Perhaps there are additional components to the universe we haven't discovered yet. Baryon acoustic oscillations, the cosmic ruler. One of the most powerful tools for understanding our place in the void comes from baryon acoustic oscillations, frozen sound waves from the early universe that have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, the sound waves froze in place. The distance these waves traveled before freezing, about 490 million light-years, left an imprint on how matter is distributed today. That distance shows up as a characteristic scale in the clustering of galaxies. Astronomers can measure this scale and use it as a standard ruler because the physics that created it is well understood. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. Using this technique, researchers have mapped the three-dimensional distribution of galaxies across billions of light-years. These maps reveal the cosmic web in unprecedented detail. They also reveal the KBC Void. When scientists analyze galaxy distributions in our local region and compare them to predictions from baryon acoustic oscillations, they find a clear deficit. The void shows up as a region where the observed scale of galaxy clustering differs from what distant measurements predict. The baryon acoustic oscillation measurements provide independent confirmation the void exists and quantify its depth and extent. The precision of these measurements continues improving with new surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. Within a few years, astronomers will know the void's properties to within a few percent uncertainty. There's another layer to this story that's worth considering. We don't just live in an unusual place, we live in an unusual time. The universe is 13.8 billion years old, and we happen to exist in an epoch when voids are prominent features but haven't yet dominated completely. Billions of years in the past, the universe was denser and more uniform. Voids were smaller and less empty. Billions of years in the future, voids will have expanded enormously, swallowing most structure. We exist in a narrow window of cosmic history when the universe has differentiated into filaments and voids, but hasn't yet become completely void-dominated. It's a time when the cosmic web is at its most intricate and beautiful, when structure exists on every scale from individual galaxies to superclusters spanning hundreds of millions of light years. This timing might not be coincidental. The formation of complex structures, planets, life, intelligence requires certain conditions. Too early in cosmic history, there weren't enough heavy elements for rocky planets to form. Too late, and star formation will have ceased, making planetary systems with stable, long-lived stars impossible. We exist in the era when conditions are favorable for complexity. Similarly, we exist in an era when cosmology is possible. The cosmic microwave background is still detectable, distant galaxies are still visible, the expansion of the universe is measurable. In the far future, civilizations arising in voids won't have access to these observations. They'll be unable to reconstruct the Big Bang or measure cosmic expansion because all evidence will have been erased by the accelerating expansion of space. From this perspective, we're incredibly fortunate. We live in a time and place where the universe is comprehensible, where the evidence of its origin and evolution is still available to study. The void may bias our measurements, but at least we have measurements to make. At least we can detect the bias and work to correct for it. If we live in a void, what does that mean for the search for life elsewhere in the universe? This question connects cosmology to one of humanity's deepest curiosities. Are we alone? The distribution of matter affects where life can emerge. Galaxies need sufficient heavy elements to form rocky planets. Those elements are created by stars and scattered through space by supernovae. Star formation needs to continue long enough to provide stable environments for life to evolve. Void galaxies might actually be favorable for life in some ways. They experience fewer catastrophic events. In dense clusters, galaxies collide frequently. Close supernova explosions or gamma-ray bursts could sterilize planets within thousands of light years. Active galactic nuclei in cluster galaxies pump enormous energy into their surroundings, potentially disrupting planet formation. Voids offer a quieter environment where galaxies evolve peacefully. Stars form at a moderate pace. Planets have billions of years to develop life without cataclysmic interruptions. The lower metallicity could be offset by the longer timescales available for chemical enrichment. On the other hand, void galaxies tend to be smaller and less massive. They form fewer stars, meaning fewer opportunities for planets to develop. The lower metallicity means the first planets to form are gas giants with few rocky worlds. Life as we know it requires complex chemistry involving carbon, oxygen, nitrogen, and other heavy elements that are scarcer in voids. The isolation of void galaxies might also limit the spread of life. If panspermia, the transfer of life between star systems, plays a role, in dense regions, material ejected from one planetary system might seed another nearby. In voids, the vast distances between stars and galaxies make such transfers nearly impossible. If other civilizations exist in voids, would they develop the same understanding of cosmology we have? A civilization in a dense cluster would observe rich structure in every direction. Their sky would be crowded with nearby galaxies. They would easily discover cosmic expansion because they could observe a large sample of galaxies at various distances. But a civilization deep inside a void might struggle. With few nearby galaxies to observe, measuring cosmic expansion becomes challenging. The void's effect on local measurements could confuse them, leading to incorrect conclusions about the universe's properties. They might develop alternative models explaining their observations without invoking cosmic expansion or dark energy. This raises a meta question. Is our own cosmology affected by our void location in ways we haven't yet realized? We think we understand the universe fairly well based on observations from within the KBC Void. But what if there are systematic biases we haven't accounted for? What if the universe beyond the void looks fundamentally different from what we observe locally? Standing back from the details, the KBC Void tells us something important about the nature of scientific discovery. Every observation we make is conditioned by our circumstances. We observe the universe from a particular location at a particular time, using instruments with particular capabilities and limitations. Our theories are built on these observations, and they inherit all those limitations. The void reminds us that cosmic truth is subtle. The universe doesn't present itself to us directly, it presents itself through the filter of our local environment. Disentangling universal properties from local effects requires painstaking work, multiple independent measurements, and the humility to accept that our initial conclusions might be wrong. The Hubble tension exemplifies this challenge. For years, cosmologists assumed both measurements were accurately capturing the universe's expansion rate. Only gradually did they recognize the possibility that one measurement might be locally biased. Even now, the debate continues about which measurement, if either, represents cosmic truth. This situation isn't unique to cosmology. Throughout the history of science, researchers have had to grapple with the question of how to separate signal from noise, universal law from local accident, fundamental truth from observer bias. The void is just the latest and perhaps most dramatic example of this challenge. What makes the void story particularly compelling is its scale. We're not talking about correcting for the motion of Earth around the Sun or the Sun around the galaxy. We're talking about correcting for the properties of a region 2 billion light-years across a structure so vast it encompasses everything we can easily observe. The bias isn't a minor technical correction. It's a major systematic effect that potentially changes our understanding of cosmic expansion, the age of the universe, and the nature of dark energy. Resolving these questions will require continued observation and theoretical work. On the observational side, the key is to extend our measurements beyond the void's edge. Deep surveys mapping galaxies to distances of 3, 4, 5 billion light-years will show whether the properties we measure locally persist or change as we probe farther into space. Improvements in distance measurement techniques will be crucial. The more accurately we can measure how far away galaxies are, the more precisely we can map the void's structure and quantify its effects on our observations. New standard candles and standard rulers, astronomical objects with known properties that can be used to measure distances, will help. On the theoretical side, cosmologists need to develop better models of how voids affect observations. This includes understanding the velocity fields they create, how they modify the apparent expansion rate, and how their presence should show up in different types of measurements. These models can then be compared to observations to test whether the void hypothesis successfully explains all the anomalies we observe. Computer simulations will play a vital role. By creating virtual universes with voids of different sizes and depths, researchers can predict what observers inside those voids should measure. Comparing these predictions to actual observations tests whether our understanding of void formation and evolution is correct. The modified gravity theories also need rigorous testing. If the KBC void is too large and unlikely to form under standard cosmology, perhaps gravity really does work differently on large scales. Testing this requires observations that can distinguish between predictions of general relativity and modified gravity theories. Measurements of how structure forms, how galaxies move, and how light bends around massive objects all provide tests of gravity. Perhaps the deepest question raised by the KBC void is philosophical. What does it mean that we live here? Are we extraordinarily unlucky to occupy one of the universe's most unusual locations? Or does our presence here tell us something important? The anthropic principle suggests that we shouldn't be surprised to find ourselves in conditions that allow our existence. If certain environments are more favorable for life, we naturally find ourselves in those environments not because they're typical, but because they're necessary. Applied to the void, this argument might suggest that void environments are actually more favorable for intelligent life than average regions, despite seeming less hospitable. The stability, the reduced radiation from nearby catastrophes, the slower pace of evolution all might contribute to conditions where life can develop and survive long enough to build civilizations. But this argument only works if voids are genuinely better for life, which remains unproven. And it doesn't explain why we'd be in such an unusually large void, rather than a more typical, medium-sized one. Another perspective is to accept that sometimes unlikely things happen. The universe is vast. It contains countless galaxies, countless voids, countless possible locations for observers to arise. With enough chances, even very unlikely events occur eventually. Perhaps we simply drew the short straw in the cosmic lottery. This explanation preserves the cosmological principle in spirit, if not in letter. It says that while our specific location is unusual, the existence of some observers in unusual locations is not surprising. Somewhere, someone had to end up in a supervoid. It happened to be us. A third possibility is that our location tells us something about how observers arise in the universe. Perhaps intelligence develops preferentially in certain types of environments, and those environments happen to be correlated with void locations. This would make our position not a coincidence, but a consequence of the conditions necessary for our existence. Distinguishing between these interpretations might seem impossible, but it's actually testable. If we eventually detect other civilizations and can determine their locations, we'll learn whether intelligent life arises randomly throughout the cosmos or concentrates in particular environments. A sample size of one us doesn't tell us much, but a sample of dozens or hundreds of civilizations could reveal patterns. Conclusion: measuring the unmeasurable. The story of the KBC Void is ultimately a story about the challenge of understanding a universe we're embedded in. We can't step outside to view the cosmos objectively. We can only observe from where we are, with all the biases that entails. The void represents perhaps the largest and most consequential bias in all of cosmology. It affects the expansion rate we measure, the age we calculate for the universe, the properties we infer for dark energy. It influences the motion of galaxies around us and the structure of space itself. It's not a minor correction factor. It's a major feature of our cosmic environment that we must account for to understand universal truth. Yet despite this challenge, we're making progress. Through careful observation, rigorous analysis, and willingness to question our assumptions, cosmologists are disentangling the local effects of the void from the global properties of the universe. We're learning to correct for our position, to see past our local environment to the cosmos beyond. This work exemplifies the power and limitation of science. We're constrained by our circumstances, trapped in a particular location at a particular time. But through reason and observation, we can transcend those limitations. We can recognize our biases and correct for them. We can build models that account for our position and predict what the universe looks like from other vantage points. The void doesn't invalidate cosmology. It makes it more sophisticated. It pushes us to develop more nuanced models, to make more careful measurements, to think more deeply about what we can and cannot know from our observations. In the end, the KBC Void is a reminder of both human limitation and human capability. We're tiny beings on a small planet in an ordinary galaxy, located in one of the emptiest regions of an incomprehensibly vast universe. We're measuring cosmic properties from inside a hole in space 2 billion light-years wide, trying to determine universal constants from locally biased observations. Yet here we are, aware of the void, measuring its properties, correcting for its effects, and piecing together an understanding of the cosmos that extends far beyond what we can directly observe. We're trapped in the void, but our minds are not. Through science, we've learned to see beyond our immediate surroundings to glimpse the universe as it truly is. The cosmos is mostly empty. We live in one of its emptiest regions. But from this desert of space, humanity looks outward and understands not perfectly, not completely, but genuinely the grand structure and evolution of the universe itself. That understanding, hard-won and still incomplete, represents one of our species' greatest achievements. We are void dwellers, yes. But we are also cosmologists, capable of mapping the universe and finding our place within it. The void may distort our measurements, but it cannot contain our curiosity or limit our determination to understand the cosmos that contains us. We live inside a cosmic hole, 2 billion light-years wide. And we know it. That knowledge itself is extraordinary, a testament to human ingenuity and the power of scientific inquiry. The journey to understand our place in the universe continues, one measurement at a time, one correction at a time, one discovery at a time. The void surrounds us, but we're learning to see beyond it. And what we're discovering about the universe, about observation, about the nature of knowledge itself, makes the journey worthwhile.